Dear users of this presentation, today we return to a non-settling discipline successfully developed in the 1970s because with the modern application of CAD-CAE systems in relation to simulation computational experiments, it takes on a new importance. The discipline is design of experiments. The object of this representation is a sought-after and desired set of combinations of control parameters has become significant when the trial and error approach loses ground. This is the period of realized need for this modeling to be applied in search of a solution through science-based approaches. When several variables affect a certain characteristic of a product, the best strategy is then to design an experiment so that valid, reliable, and reasonable conclusions can be drawn efficiently and economically. It is important to note that not all variables affect quality indicators in the same way. If we have to briefly describe what design of experiments is, then the words a set of combinations providing optimal characteristics can be successfully used. The optimality of the features is in terms of the accuracy of the solution and the cost of the experimental resources. These two characteristics are contradictory, and this explains the plethora of authors who have sought and proposed the solution. The interest in the problematic of the set of necessary trials subordinated to a goal, introduced in 1920 by Fisher, but really started to operate since 1951 after the publication of an article by Box and Wilson. This interest is great because it is a means of reaching the global economic optimality criterion. The private optimality criteria are subject to certain quality criteria, and they are also directly related to the goal. In addition to the potential and the approach, further significant applications can be mentioned, such as improved process yield and stability, improved profits and return on investment, reduced process variability, reduced production costs, reduced process design and development time, increased profitability of the business by reducing scrap rate, defect rate, rework, retest, etc. Purpose of this presentation is to outline the differences between known and used experimental designs with control factor numbers 2 to 5, and thereby show prospective experimenters how to organize their experiments. For the modern technique, when speed and power are ensured, the idea of how to include new combinations in the experimental series in the organization of the simulations aimed solely at increasing the accuracy of the solution is important. The graphical part of the presentation actually shows what coded values of the new experimental combinations can be used. This idea is proposed for use in simulation computational experiments only. This provides a modern reading of the existing computing technologies adapted in the present for the new working conditions using CAD-CAE systems. Solving this is unthinkable without the introduction of coding. Through coding, regardless of the plan, ideas that have not lost their relevance until now can be shared. Experimental designs such as full factorial, optimal compositional, orthogonal central compositional, rotatable central compositional, Hartley plan, Pezuchinsky plan, Box-Dapper plan, and successful D-optimal plan have been considered. The sequence in the implementation of the approach is as follows. From the goal we have set for ourselves, we compile a statement of the task. This staging contains the parameters that govern the process. These parameters affect the quality indicator or indicators. The latter are the object of the research. Second, a range is chosen for varying each of the parameters, and the limits of the range are determined according to the value of the quality indicator. The figure shows the scheme and the key for encoding and decoding the factors. This operation is extremely important in terms of keeping the innovative solution. With these two keys, the research stakeholder initially encodes the factors, and finally, when he is provided with a solution by the computing team, the stakeholder decodes the solution. Third, a main effects plot is drawn to compare the relative magnitude of the impact of the control factors on the quality indicator. An example of the effect of 8 process parameters on porosity is shown. From the analysis of the graph, it can be determined that the influence of the parameter A is the weakest. It and parameter D can be neglected in the research. The parallel lines of influence of parameters B and C mean that they are linearly dependent, and therefore one of them must necessarily drop out. The remaining parameters in the research are called factors, and thus the problem from the above-mentioned example is reduced to the research of 5 factors. Let's apply the first and second points of the above-defined plan to a well-defined example. The goal we have set for ourselves is to implement let us The goal we have set for ourselves is to implement a mode of laser marking technology that, while printing quality images, is productive over time. Based on the example, we introduce the following clarifications related to points 1 and 2. Control factors, power in the range of 10 to 30% and speed in the range of 100 to 300 millimeters per second. Quality indicators, elaboration time seconds, and image quality in percents. Quality indicator identifiers, time should be shorter, so its identifier should be minimal, and quality should be relatively good, and its identifier should be maximal. The research object is that laser marking process related to the specified quality indicators. Fourth, most often the goal we set ourselves is optimization of quality indicators, whereas it is necessarily to determine where the compromise solutions are located and what their value is for the set identifiers. In these cases, it is necessary to derive models of the influence of factors on all quality indicators. An example solution to this task is presented in the table. It defines the optimal solutions of the indicators and the values of the factors at which this solution occurs. The determined values of the factors form the optimal technological mode. Fifth, when the question of the regression model becomes relevant, it is necessarily connected with the experimental plan according to which the model was created. The use plan depends on the number of factors and the degree of the model. The attached figure shows the most basic design for a full factorial experiment with 2 levels of change. Levels are -1 and +1. The diagram shows the way how from the unit cell with a 2-factor plan containing 4 combinations, a 3 and 4 factor plan is made. The important thing to know is that this simplicity of the plan also creates a simple incomplete quadratic model with only mixed interactions. The above plan serves as the basis for all other plans. So, for example, if for 2 factors an optimal compositional plan is to be compiled, then these 4 combinations of the core of the plan are supplemented with 4 more containing the middle zero of the variation interval. The new plan thus drawn up is, however, able to offer a model of the second degree. This model would be more accurate if the plan is centered, i.e. also contains a nice centered combination composed of the midpoints of the variation intervals 0, 0. Let us now return to the question of what possible experimental combinations can be included in the design so as to improve the accuracy of the simulation experiments. We will do this through special coded values of 4-factor plans. Another question is whether these combinations can be implemented. But yes or no, the interest expert must know about this possibility in order to possibly use them. We will focus our attention on the features of plans that enable the construction of second-order models. The first possibility that needs to be technologically checked is whether changing each factor by 1 full step from below the interval to -1 and +1 above the interval in different combinations can give acceptable and sustainable results for the studied quality indicator. If this is possible, then several unmatched combinations containing the coded value +-2 can be borrowed from a rotatable central compositional plan. Another feature of this plan is that it contains 7 identical centered combinations. This in a numerical experiment is not applicable because the standard same combinations will always give the same simulated value of the quality indicator. It has been statistically proven, however, that in real experiments with reported differences, this improves the accuracy of the sought solution. In the event that it does not make real sense to the coded value, plus minus 2 for any of or all of the investigated indicators, then resort to a check for the possibility provided by an orthogonal central compositional plan with a coded value of plus minus 1.4142. These two coded values also fall outside the predetermined variation interval. In the event that it makes sense to them with a real and reliable result, then the four-factor plan can automatically be expanded with 8 new combinations. The table contains information without plans with a suggested minimal number of experiments. One of them is box and uppers plan. It is statistically derived and coded values 0.6502 and plus 1.4114 are suggested in its derivation. The proposal is about what additional combinations in this connection can be included by this plan, and in principle be considered at all. In the table, information is collected and indicated about the total number of attempts to be made. From the table, it can be seen that the minimal number of attempts is 15 for box and upper, and the maximum is 81, which, however, is related to the third degree. Similar tables were compiled for 3 and 5 factors. Similar considerations apply to them. The corresponding coded values for these factors are indicated, and the number of experiments required is given by the proposed author. As a summary, this information is listed in a table showing the results of this review. For the second-order models of the number of explored factors, different experimental designs were compared to determine the minimal and maximal number of experiments, and the particular coded notes in these designs were also indicated. As it was explained, after the experimental plan is drawn up, the experiments are carried out according to it. And the models are derived, and if they are adequate, then it is switched to their analysis and optimization. And our laboratory, named after the corresponding member, Professor Lubomir Kalev, has accumulated experience in solving these questions. For all who have similar problems to solve, we can be available. We have the opportunity to participate in your projects and contribute to them as part of a team or in our work independently of the team. Thank you for your attention and time.